Thank you. So yeah, it's been a couple of months that we've been analyzing the call-side behavior of Ruby applications. And so today I'm going to be talking about the conclusion of this analysis. And so as James told, it's a joint work together with Octave Larose, Richard Jones, and Stefan Ma from University of Kent. So what we did, so we analyzed 74 Ruby benchmarks. Our benchmark set is pretty diverse. So we have smaller micro benchmarks, and we have larger industry-inspired benchmarks, web apps running on Ruby on Rails. And so I said we're looking at call-side behavior, and by this, so we use the type of the receivers at each call site to represent call-side behavior. And what we analyzed is, what we looked at is polymorphism. We also looked at how existing call-site optimizations are impacting call-side behavior. And we also analyzed how call-side behavior is changing at runtime. And so first, we had a couple of assumptions in mind that are, well, commonly accepted in the field as, well, being true. First one being that most calls at runtime are monomorphic, which means that at a given call site, we will always call the same target. Second assumption is that in classic object-oriented programming way of developing, you end up with kind of a, well, significant amount of target duplication in caches. Third assumption that we looked at is the fact that common call site optimizations usually helps monomorphizing caches, which means that if you have several entries in one cache at a given time at execution, then after those optimizations are applied, you only have one entry after. And the third assumption what we checked is that industrial benchmarks are, well, they tend to be a bit larger, they tend to have bigger caches, and we checked whether that was holding, at least in our benchmark sets. And, well, they were all true, actually. So in our benchmark sets, our 74 benchmarks written in Ruby, we had around, let's say, on average, 98% of calls that were monomorphic. So, okay, so that's one thing. So we also had a significant amount of duplicates in lookup caches, I would say around, I don't know, 40 to 60% of duplicates in caches. So we looked at two kinds of call site optimizations. So the first one actually tried to get rid of those duplicates in caches. And the second one is splitting, and I'll just explain in a bit what this is. So we looked at those optimizations, and indeed, they were very effective at monomorphizing caches, so that's super great. But yeah, so it's checked as well. And so as I said, as well, our benchmark set is pretty diverse, and we had, well, bigger benchmarks that are used in industry and try to reproduce the industrial setups. And those were the benchmarks in our set that were indeed larger with bigger caches. Whoop, doesn't work quite well. So it's great, but did we find actually something new? Because those assumptions, so because they were commonly accepted, if they're all true, that's not very interesting. And yes, of course, we did find some cool stuff along the way. So I will now just describe three, well, interesting things that we found. And that could be, starting point for new optimizations, for instance. So the first one is that splitting, so this call site optimization that I talked about just before, is super enthusiastic, but maybe a bit too much. So I said we analyzed Ruby applications. It's Ruby running on top of GraalVM. And so TruffleRuby has dynamic dispatches and lookup caches. And so what a lookup cache is, well, So I have this stupid snippet of code. You have a collection here containing different kind of pets. You iterate on this collection, and each pet has to shout. So say on the first iteration, and this is on the right, this is a very simple, say AST, so that's a node on the AST representing the call site for shout. So on the first iteration, Gomez has to shout. Gomez is one of my cats. And so, which means that in the lookup cache here, so we'll have one entry for this target, which is shout for cat. Okay. And right now the cache is monomorphic. And so caches here, they are pretty useful because it means that if on the next call to this call site, if you happen to want to execute the same target, then you don't have to, resolve the lookup and so on. It's already in a cache. And that's actually what happens on the second iteration of this loop, because Rufus is actually my second cat. And so we don't need to actually, add a new entry in the cache because the target is already there. And then third iteration, Onai is actually not a cat. And so then the cache will turn polymorphic, which means that we will add a new entry in this cache. And we don't quite like polymorphic caches. So it's pretty useful, but also it has kind of a, negative aspects of it. First, of course, the more entries you have in the cache, the slower it will get to actually resolve the call. And of course, there are always edge cases. So what if you have these call sites and the most frequent target you want to execute is like the last in your cache? Well, that's inconvenient. And most important, I think, once you have a polymorphic cache, then when you want to align these call sites, it won't be as easy for the compiler. So, splitting to the rescue. Splitting, what it will do, so it's a call site optimization, and it will try to get rid of polymorphic caches. So what it does, in TruffleRuby at least, so it will clone a call site, such as the uninitialized version of the AST for this call site is used. So here I have a slightly more detailed version of the AST for the same stupid snippet of code. And so we are using this bit of AST so far. Then the cache turned polymorphic, which is a signal to the system that it's time to split the call site. So we split the call site, and what happened is that now we have this new version of the AST that, an initialized version of the AST that is used with a brand new empty cache. And that's the path we'll take in the AST from now on. And so, as said, it's generally triggered when the cache will turn polymorphic. It will reset the cache. And ideally, if we consider that, the behavior of the program is pretty stable, it means that since we're now relying on this new empty cache, that ideally at least it will stay monomorphic for the rest of the execution. So we checked this. So here you're seeing 5 benchmarks that had the most important number of polymorphic calls. So in our benchmark sets. So on the leftmost column, so we have the number of polymorphic calls before all optimization. In the middle column, it's after a couple of call sites optimizations. So you can see that the numbers of polymorphic calls have reduced, but it's not significant. But after splitting, it's pretty amazing because we mostly have no polymorphic calls at all. So that's great. So splitting is very effective. We kind of very much get rid of polymorphic calls. But we had a look at something else. So let's say, again, same stupid example. Well, when you think about it, what you want when you split a call site, you want that the cache content between the original version and the split version, you want those two caches to be different, because if they stay the same, well, it means that maybe split was unnecessary. And so we checked for each time a split happened, whether the cache content between the original version and the duplicated version, well, we checked whether those caches were different. And the results here were surprising, because so for the same 5 benchmarks as before, then we have a very large amount of split that, well, ends up with having caches that are the very exact same between the original version and the duplicated version. And, well, so we investigated this a bit. So yeah, as I said, we kind of very much expect that the content of the cache will differ between the two versions. So this may suggest that we actually oversplit. So if we have, for instance, in the first benchmark, we had 60% of splits that ended up having the same caches, well, maybe then we didn't need to duplicate them in the first place. So maybe we're oversplit, and if we do, it means that then maybe we're using much more memory than we should. And we investigated a bit what was causing this, and yeah, sometimes splitting, so the fact that we duplicate call site, or that we clone call sites, is propagated in the color chain, and this seems to be one of the sources of this seemingly unnecessary splitting. So we're still, well, investigating this. I'll talk about it a bit later. But yeah, so that was the first cool thing we learned from the analysis. On to the second thing. Remember I said, oh yeah, splitting is super cool, especially if the call site behavior is stable. Well, it's not necessarily true. Well, usually we talk about the fact that there is an initialization phase, and then the program, the behavior stabilizes. Well, it's a bit more complex than that, again, in our benchmark sets. So what we did is that we focus on polymorphic call sites before splitting, because otherwise they're all monomorphic, so it's a bit less interesting. And we traced when different targets for a given call sites are called at runtime for the call sites that are the hottest one at runtime. And we identified, so we found 3 different patterns of behavior. First one, of course, is the initialization one. I mean, it still exists. So how you should read this plot: on the x-axis, you have, so each dot represents one call. And so on x-axis, it's the call ID. So here we're looking at this reassignment call in this file at this given line. And here you can see that it's, it's called on 2 different targets, the one for array and the one for versioned array. And so here you can see that at the very beginning of the execution, we are calling only the version array targets for a couple of times. And for the remaining of the execution, we are only calling the array version. So it's not great if you consider caches, because obviously it means that somewhere after the starter phase, you have 2 entries in the cache while you really just need 1. But yeah, so that's one of the patterns we identified. The second pattern is a phased pattern. I said, so that's a kind of a simplified plot. So it's very polymorphic, but I just kept the interesting target here. So again, we're looking at a call to nil or empty in this file. And you can see that it's kind of behaving, it's not called exactly the same way through her execution. So you can see a first phase where this target is called, well, a bit often, but it's the calls are a bit spread. And during the second phase, then you have much more frequent calls to this target. So here, phase execution. So it's here it's a difference of frequency. It could be something else, but well, we can see two different phases here. Okay, so I said 3 patterns, that's 2. Third one is the mirroring pattern. So again, the comparison here in this file. And here you can see that the 2 targets are, well, they are behaving mostly the same. So we have symbol and basic objects, and they are behaving the same kind of during the whole execution. Of course, those different patterns, they may mix. So here, for these call sites, you can see that we have phase pattern for those two targets. We also have a mirroring pattern. So of course, they may mix. And sometimes there's no clear pattern that can be identified at runtime. So yeah, so it means that, well, the behavior is not necessarily stable. Still, well, the fact that the behavior is stable is one common assumption that is used to build optimizations. Well, we had to look at 2 optimizations, and namely splitting that is, well, built upon this optimization, and they're still pretty effective. So it doesn't mean that it will kind of invalidates all the optimizations that are based on this assumption, but maybe we could reuse this knowledge to, well, create new things. So third and last point. So we had a look at the difference of behavior between closures and methods. And we found that they're not behaving quite the same well, in terms of polymorphism. So just a quick reminder, so in Ruby, closures, they're called blocks, and blocks are both procs and lambdas. Basically, they're just anonymous functions. Lambdas, they're standard methods, and with a kind of stricter argument check. And the procs, they're a bit more relaxed with mismatching arguments. I won't make the difference between the two anyway in the next tables, but that's how it works in Ruby. So we looked at the difference in terms of number of polymorphic calls, for instance, between methods and blocks. Here, it's not the same 5 benchmarks as before. I picked the 5 benchmarks that had the most important number of polymorphic calls for blocks. So here you can see that, for instance, Havlac had less than 1% of polymorphic calls. But when you see, so methods, I'm talking about methods here, but when you look at blocks, then you have a much higher frequency of polymorphic calls. And that's, well, the same for those 5 benchmarks. It's not the case for all of our 74 benchmarks, but yeah, there is a trend in which blocks tend to be more polymorphic. And well, the other thing is, so I'm looking at one extreme. So here I was looking at the most polymorphic benchmarks for blocks. If you look at the least polymorphic benchmarks for blocks, well, we have as well, kind of a similar pattern. So for blocks, the least polymorphic benchmark still has 2.1% of polymorphic block calls, while it's less than 1% for method calls. So it's not working. That's great. So yeah, as I said, we had assumptions that were validated. That's great. For those that were different or that we didn't expect still, well, that's great, because that might indicate that there is optimization opportunity. So what are we going to do about that? Well, remember that I said I would talk about splitting a bit, which I'll do right now. So we started working on something called context-driven splitting. So it's It's kind of based on contextual dispatch, which is a paper by Fugger et al. And so the idea is we want to use contextual knowledge, could be argument types, could be return types, could be the content of the query chain, could be a lot of things, just contextual insights to guide splitting with two goals. The first one would be to actually limit splitting, because we assume that we're over-splitting at the moment. So maybe if we manage to guide splitting decisions a bit better, essentially if we manage to identify when a split is unnecessary because we will keep the same content in the cache, then yeah, maybe that would be beneficial. And one other thing that could be used with context, that could be the outcome of context-driven splitting, is that maybe we could manage to share specializations for a same context. So I started working on this. This is still very, very early work. I'm happy to talk about this later, but I won't go through the results of this right now. So, and that's actually basically the end of my talk. So remember, we had those assumptions. They were verified, so we were very happy, but we found very, well, cool, interesting things along the way. We found that we were most probably over-splitting and that maybe we will do something about it. We found that there are patterns of call-side behavior, and that the behavior of programs is not necessarily stable. We found that there are differences in behavior between methods and blocks. So that's still pretty exciting, because it means that there are still ways to find new optimizations opportunities. So I talked about context-driven splitting to tackle these oversplitting problem. For phases, well, there have been attempts in the past to use high-level, the insight on high-level behavior to guide optimization, but maybe we should have, well, a closer look now in nowadays context. For blocks, yeah, maybe we could find new optimizations that are specifically targeting blocks. So yes, yeah, I mean, I still think that's pretty exciting. So thanks for listening, and I'm happy to take any question.
Thank you for the talk. I'm interested in the patterns that you found, and
Yes.
For example, for the init pattern, you showed, for example, the I think it was the truffle base array or something, and then it switched over to a Ruby array. Or
No, which one was
init,
this?
the first one.
Oh, yes.
Yeah, the truffle version array, and then it used the array. So I was wondering, for example, how much of those patterns, or like how many instances did you find where the pattern might be caused by the specific implementation of the runtime, and in particular, for example, the truffle runtime here? Or would you see the same, or ask differently, would you see the same pattern, let's say, in the same frequency in other runtimes, in other Ruby implementations?
So I haven't looked at those at other Ruby implementations, but so here indeed you see this pattern, and you see that the one that is causing the extra unwanted entry in the cache is caused by truffle. We have in our benchmark set, we have other instances of this pattern in which truffle-related targets are inexistent. So still, I can't, well, quite clearly answer your question, because I don't know. But here, the fact that it's caused by a truffle target is not the case for every instance of this pattern that we found in the benchmark set.
Okay, So you're saying it's just a minority, and that's like just the example that.
Yeah, it's just the example. There are other instances of this pattern that were not containing truffle-related targets.
Mm-hmm. And the second question, if you allow, on the I think it was the mirroring pattern or the third one. Do you see that, for example, for code that delegates a lot, or either in the runtime or in some frameworks?
So I haven't quite had a look at what could cause this. So I'm not sure. I mean, I can have a look. If you want, we can have a look together after the talk.
Okay. Thank you.
Yeah, interesting talk. I'm aware of contextual dispatch in general, so I was just wondering what would be the context in the context-driven splitting. I probably didn't get it when you said. What is the abstraction that would define a context in here?
So the idea, so what we started to investigate with this, the very, very naive starting point with this would be that maybe if, so we'll start just focusing on argument types. Because that's just very naive and that could work pretty well. So say that you start, you have a call site, you call this call site with a specific arguments that have specific type. Then this call site at some point gets split, which means that it has to be called a second time. And so what we will try to do first is to check, so basically if the second call is having the same arguments, then we will consider it's the same context and we will not split. So right now, I'm not sure whether that will lead to something useful or completely stupid results. But that will be the very first step of context-driven splitting.
Yeah, makes sense. I mean, you're splitting based on the types, so makes sense. Thanks.
Right, well, it's probably time to thank the speaker again.